5G has been all over the media for quite a time as a catalyst of change for business as well as society. According to prevailing gospel, its significance compared to the utilization of electricity with an endless strike of opportunities. As you may sense, my view on this is a bit more nuanced. Actually, 5G does not deserve this attention on its own merits, but rather as an important leg in the bigger narrative called digitalization. Digitalization is about the collection, structuring and utilization of data to develop new services and improve existing operations. In order to collect this data from mobile units and other geographical dispersed items, a modern mobile network is required with focus on machine-to-machine communication. In our time, digitalization has become an imperative, allocating vast amounts of human resources as well as capital. The potential outcomes of these efforts may not always be clear, but no one wishes to be left on the sideline of this megatrend. It is worth keeping in mind that both 4G as well as 5G relies on radio technology limited by laws of physics, whatever the marketing hype projects. There are lots of misconceptions out there in the technical merits of 5G, amplified through the echo chambers of the internet until it become alternative facts. The third generation partnership project, or 3GPP, is an umbrella term for a number of standards organizations which develop protocols for mobile telecommunications. As can be seen from the numbers, this is a huge undertaking requiring massive global cooperation. Some may be surprised to find it's dominated by Europe and Asia, but then again, recall company names as Ericsson, Nokia, Samsung and Huawei as the major infrastructure providers. 3GPP Group develops standards which evolve through an overlapping pipeline. The first 5G release is Release 15, although some of the features projected for 5G already were put in place in Releases 13 and 14. The full 5G feature set is likely ready as of Release 17. Note that the deployment schedule will depend on operator plans as well as national regulations. This may pose a problem for customers with a global scope depending on a given 5G feature set. The 5G playbook as provided by 3GPP exhibits three main topics: enhanced mobile broadband, massive machine-type communication, and ultra-reliable and low-latency communications. These topics mark both an evolutionary approach from 4G as well as features unique to 5G. Enhanced mobile broadband, which is brought forth in Release 15, defines phase 1 of the 5G development. EMB represents an evolution from 4G with respect to capacity and speed, but it also employs a totally new radio. In mobile communications, frequency spectrum becomes the prime asset, leading MNOs to pay billions of dollars for the right to operate within dedicated parts of it. The spectrum below 6 GHz is pretty crowded, but provisions has been made by national regulatory bodies in order to accommodate part of it for 5G use. Moving up in frequency accommodates an increasing number of smaller cells due to higher signal attenuation and consequently a higher total capacity over a given geographical area. Speed in the lower bands is on par or somewhat higher compared to the best 4G networks. The millimeter wave bands support higher bandwidths, but is likely unpractical for mobile clients. The prime target is likely to become fixed mobile broadband, or if you like, cable replacement. Typical rates achieved for frequency range 1 sub 6 GHz bands for 5G will be from around 100 to 400 megabits, which is a bit higher than for the best 4G or LTE advanced networks. The next leg would be massive machine-type communications, which are partly present in Release 14 as well. Not much new here compared to 14, but it's possible to pack more devices into an area covered by a cell. Optional relaxed signaling requirement also may improve battery life for connected client devices. Ultra-reliable and low-latency communications is considered to be the real 5G deal, starting off with release 16. And probably not achieved until well out in the release 17 timeframe. It's an adaptation to the needs of more professional use versus traditional consumer-based use. Quality of service will be available and linked to service level agreements where you pay from what you get from a given quality level. It will require architectural extensions to the mobile network and heavy investments, and it will take time. A typical transaction pattern as of today is user equipment making a request to a cloud-hosted server generating northbound data packets. The server typically makes some intra- or inter-cloud transactions upon finally sending reply packets southwards. The transaction will thus traverse a significant number of routers and servers, adding up to a noticeable delay termed as latency. In the case that all we wanted was to send a direct message from one user equipment to another user equipment within the same radio cell, this is clearly not an optimal solution. In order to reduce latency, additional routing resources must be added, cutting down the distance data packets needs to traverse. Intra-cell routing should be default, and fast inter-cell routing must be provided for coordinated mobile units which may be either in the same cell or in adjacent ones. For practical applications, direct client-to-client communications does however not cover all use cases, and server resources will need to be deployed at the edge. One could view this as a physical extension of cloud computing, and in fact this already has a name: fog computing. Regarding 5G latency, 1 millisecond is often mentioned in the media, but this is in fact only a 5G goal for latency added by the 5G radio itself. In 5G as well as 4G, three counteracting parameters come to play: latency, reliability, and bandwidth. If you want higher reliability, more retransmit time slots must be added, resulting in higher latency and lower bandwidth for the other queued packets. On the other hand, choosing lower latency means shorter time slots and shorter packets and more overhead, resulting in reduced bandwidth. If you want it all, you're out of luck. Following up on latency, shorter time slots, TTI or transmit time interval, is already available in 4G release 14, as shown in the diagram provided by Ericsson. This is also the case for fast uplink, providing the client a grant each milliseconds versus traditional scheduling requests, SR. As can be seen, the real improvement took place going from release 13 to 14, and may thus be available in updated 4G networks. There are obviously some cost implications for shorter latency, given that radio efficiency and thus the overall capacity decreases. A customer requiring this for general public shared cells will probably have to pay a high premium. Using private cells and 5G network slicing is maybe a more realistic scenario. Digging into features new in 5G, network slicing is likely to become the prominent one. It may offer the quality of service and robustness required by, for instance, emergency services. For military use, the possibility to operate with private cells and isolated networks may offer the flexibility and the resilience required in addition to the quality of service enhancements. For an automated factory employing both fixed and mobile assets, network slicing opens the possibility for a coherent managed local area network, whether connected over cable or radio. One might say this represents the final important step in data and telecom network conversions. Onto the business side of this will we find virtual network slice operators. And might these become today's major cloud providers, given the services offered in 5G is a natural extension of today's cloud-based services? Thank you for your attention.